Hello! Yes, and welcome to our Objective 3.7 notes. Objective 3.7 says I can graph logarithmic functions, and that, my friends, is going to be what we do today. So let's start talking about the standard form of a logarithmic function. So a logarithmic function is written in the form y equals log base b of x, right? My variable is in the argument. Now, all logarithmic functions have a vertical asymptote. And you might think, well, that's strange. Think about our exponential functions. They all have a horizontal asymptote. Right, remember that these are inverse functions. So there's going to be some similarities, but they're often going to be switched. So whereas the exponential had a horizontal asymptote, the logarithmic will have a vertical asymptote. Now, if the logarithmic function is not transformed, that vertical asymptote is at the equation x equals 0. Now, the domain of a logarithmic function depends on the vertical asymptote. In this case, if we have an untransformed function, it'd be 0 to infinity. The range of a logarithmic function is always negative infinity to infinity. Again, think about how this relates to our exponential functions. The logarithmic function has a domain that's restricted and a range that is unrestricted. The exponential function had a domain that's unrestricted and a range that is restricted by the asymptote. So let's go ahead and plot some points here. So what we're going to do is we are going to plug in some values. So log base 2 of x of 0. So let's go ahead and try to put this into our calculator. Log of 0 divided by log of 2. Notice what happens. We get an error message. Remember, our argument has to be greater than 0. So there's no answer there. It's not applicable. Now let's try log of 0.25 divided by log of 2. See what happens here. If we did it correctly, we get negative 2. And as we go fill in this table, this would be 1/2, which would be 2 to the negative first. 2 to the 0 power, of course, would give me 1. 2 to the first would give me 2. 2 to the second would give me 4. 2 to the third would give me 8. 2 to the fourth would give me 16. 2 to the fifth would give me 32. So notice, as x increases, y increases, but at a slowing rate. So the more we increase x, the slower our output increases. So notice from here, we need to increase by 2 to get up a whole unit in our y, but here we had to increase by 4 to get up a whole unit. So let's see what that looks like on our graph. So if I plot these points here, I would have an asymptote at x equals 0. All right, we had 0, we had the point 1, 0. At x, when x was 1/2, we had negative 1. X is a quarter, negative 2. We'd have the point 2, 1. We'd have the point 4, 2. We'd have the point 8, 3. That'd be here. So notice the relationship that we have here. This is our basic form of a logarithmic function. So notice, our asymptote is at x equals 0. Our domain would be 0 to infinity. And our range, in this case, would be negative infinity to infinity. It's going to go up forever. It's just as it keeps going up, 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 it's going to be slower and slower and slower. It goes to infinity. It just takes quite a while to get there. All right, so let's look at some transformations we might have here. So for this one, we have, of course, a vertical transformation on here, our vertical shift on the outside of the argument of the logarithm. Our horizontal shift is on the inside of our logarithm. And for this one, the stretch of compression occurs also on the inside of the argument. Now remember, the argument of a logarithm has to be greater than 0. And that's how we find our domain. We set ax plus or minus c, whatever is inside the argument, greater than 0. So what we're going to do for now is just find the vertical asymptote, the domain, and range. Now you might be saying, Mr. Carter, how do we find the vertical asymptote? Well, remember the relationship between the vertical asymptote and the domain. If we find the domain restriction, we find the vertical asymptote. So looking at letter A, my argument is 4x minus 3. I know that 4x minus 3 has to be greater than 0 because my argument has to be greater than 0. So I can say 4x has to be greater than 3 when I divide by 4. That tells me x needs to be greater than 3/4. So 3/4 is the value of my vertical asymptote, and it's the lowest value in my domain. My range, of course, is always negative infinity to infinity. Let's look at that again. So my argument here would be 3x plus 1 for letter B. I'd say 3x plus 1 has to be greater than 0. So that means 3x has to be greater than negative 1 when I subtract 1 from both sides. I divide by 3. So that tells me that x has to be greater than negative 1/3. So my vertical asymptote would be x equals negative 1/3. My domain would be negative 1/3 to infinity. And my range would be negative infinity to infinity. Of course, every time. C, our final one here. Again, all we have to do, argument. It doesn't matter if it's a log or if it's the natural log. It doesn't matter what the base is. The argument has to be greater than 0. So I say 6x minus 1 must be greater than 0, which means 6x must be more than 1. Divide by 6. That means that x must be greater than 1/6. So my vertical asymptote would be at x equals 1/6. My domain, 1/6 to infinity. And my range, of course, negative infinity to infinity. So let's talk about now finding the intercepts. Now, of course, we can do it algebraically. Remember, to find our x-intercept, I set y equal to 0, solve for x. To find my y-intercept, set x equal to 0, solve for y. And of course, since they are intercepts, they need to be written as coordinate pairs. This probably looks very similar to what we discussed with exponential functions. Same rules apply. We can also use our calculator. So let's do this one together here. We're going to go ahead and do letter A and review the steps. This is just like what we did with our exponential functions. Same exact process. So I'm going to go to y equals. I'm going to type in the equation. So this one is the log of 2x minus 5 and then plus 3. I'm going to hit graph. So I type my equation into y equals. I click graph. Okay. So notice here. Think about my domain restriction. Right? 2x minus 5 has to be greater than 0. So I'd say 2x has to be greater than 5. So that means x has to be more than 5/2, which is what we see in our graph here. It looks like it stops right at 2.5. If x is more than 5/2, I'm not going to cross the y-axis, am I? So my y-intercept here will not exist. Now, one of the tricky things here is your graphing calculator. Remember, it's a machine. It can't logically process things. It just follows coding. So it looks like the function stops here. It looks more like a square root function than anything else. However, we know what's happening here is the function is just so close to the asymptote that it's not showing up. That doesn't mean it doesn't exist. Remember, the range of logarithmic functions is negative infinity to positive infinity. This one does indeed go to negative infinity. We're just not seeing it on the graphing calculator. So a fun thing we can do is click second, calc, 0. Check this out. You say, well, Mr. Carter, it doesn't cross the x-axis. It clearly doesn't. I'm going to press enter before I reach it. I'm going to press enter here. What do you know? It still gives me a value. It does indeed cross. It's just it's so close to the asymptote that the graphing calculator physically does not have enough pixels to show how close it is. So, again, what I did there, second, calc, press number 2, which is 0, and enter. I set my left bound. I set my right bound. I press enter. And then, of course, the x value. is the x-intercept in the function. So this one would be 2.501. Now, we just round to the nearest hundred, so we're going to say 2.50 comma 0. Even though that is the value of the asymptote, we know we're rounding here. It checks out. Now, we can also do this using algebra. So let's go ahead and try to do this with some algebra. So if I want to find my x-intercept, remember I set y equal to 0, or f of x in this case, so 0 equals the natural log of 3x plus 2. And then I just solve this equation. So I already have isolated my logarithm. I can rewrite this as an exponential. So it would be e to the 0 equals 3x plus 2. Right? My base is e. So anything to the 0 power is just 1. So 1 equals 3x plus 2. I subtract 1 from both sides, or sorry, subtract 2 from both sides. So I will get negative 1 equals 3x. Divide by 3, and I find that x equals negative 1/3. So my x-intercept, negative 1/3, comma 0. Now to find my y-intercept, I need to set x equal to 0. So I'd say y equals the natural log of 3 times 0 plus 2. Anything times 0 is just 0, so I would just have the natural log of 2. So I'm going to close out of this in my calculator. The natural log of 2 equals 0.69. Nice. 0, 0.69, close parentheses. There's my coordinate for my y-intercept. So what we're going to do now, we're going to combine what we've done. We're going to put it all together. We're going to graph these functions. So we're going to state the x-intercept, y-intercept, asymptote, domain, range. Here we go. So let's start with our domain and asymptote here. I see x minus 1 must be greater than 0. That means x must be greater than 1. So my asymptote is at x equals 1. My domain would be 1 to infinity. My range, as always, negative infinity to infinity when we're dealing with a logarithmic function. Now think about it here. If I have an asymptote at x equals 1, like I do right here, and I'm to the right of this function, or to this asymptote, I'm to its right, that means I will not have a y-intercept. My graph will not cross the y-axis. Let's go ahead and put this into our calculator. Now putting these logarithms with different bases into our calculator can be a little tricky. I'm going to use parentheses here. So I'll do log of my argument, x minus 1, divided by log of 4, close parentheses, and then close the parentheses for the entire logarithm, plus 4. Press enter. Oh, sorry, press graph, and here's what I see. Fantastic. So let's go ahead and second calc my x-intercept. So I need that 0. Remember, it's going to be less than 1. I need one that's more than 1, and we find it to be, oh, no sign change. Interesting. So that means it's so close that it's going to identify it. Let's check the table here. Yeah. Interesting. Right, and notice how it says error here. Notice how it says error here. So that means that through all of this, through all of these things, there's no value, right? Because everything has to be to the right of 1. So to find our x-intercept, we're going to have to use some algebra here. So let's go ahead and mark my table that I can. Let's see. I'm trying to find values. Okay, there's a few values here. So this one I'm definitely not going to keep in order because that wouldn't be very helpful. But I do see 2 is a helpful number, 3 is a helpful number, and then 5, that's pretty helpful. 5 is 5, so I have 4, 4.5, 5, and then I thought I saw one more. 9 is 5.5. So there's 4 values there that I can graph. That'll be pretty helpful. Let's find the value of our x-intercept. So this is going to take some algebra. So remember, to find my x-intercept, I set y equal to 0. So I'll say 0 equals log base 4 of x minus 1 plus 4. Oh boy, I can see why it didn't work out. I need to subtract 4. So negative 4 equals log base 4 of x minus 1, which means in exponential, this would be 4 to the negative 4th equals x minus 1. So when I add 1 to both sides, it will be 1 plus 4 to the negative 4th power. Let's put that in our calculator. 1 plus 4 to the negative 4 is going to be very close to 1. 1.00 when I round, in fact. And that's why it wouldn't show up on our calculator. We couldn't get that value in there. So 1.00 is basically right here. I'm at the points 2, 4, 3, 4.5, 5, 5, and 9, 5.5. That would be right here. And then I can create my function. Now it's important that we show our arrows here. All right, let's look back at our graph. The graph looks like it stops before it even reaches the x-axis. Remember, our range is negative infinity to infinity, so it continues to go down. That's something where you need to be sure. You need to be sure that you show the arrow of it going down, okay? Let's try another problem. The natural log of 5x plus 2 plus 1. Okay, so the natural log of 5x plus 2. Let's find asymptote domain range. So I'd say 5x plus 2 needs to be greater than 0. So that means 5x must be greater than negative 2 divided by 5, and I find that x must be greater than negative 2/5. So that means my asymptote is x equals negative 2/5. My domain would be negative 2/5 to infinity. And my range, of course, as always, negative infinity to infinity. So let's put this into our calculator. So I'll say the natural log of 5x plus 2 and then plus 1 and hit graph. This time it definitely looks like we have a y-intercept. The x-intercept is going to be right around there. Let's see if we can calculate that x-intercept. I'm not sure if we'll be able to. Let's go to negative 1, press enter. We'll see if it picks it up here. Yes, it is. Negative 0.35. So my x-intercept, negative 0.35, comma 0. I'm going to go ahead and try to graph my vertical asymptote here. That's about negative 2/5. Again, precision is difficult here. So there would be about my x-intercept, negative 0.35. To find my y-intercept, I can use my table. See if we got, and since we're dealing with e, we're not going to get many good values here. So let's just go 0, 2, 4, 6, 8 and see what happens. So at 0, we're at 1.69. And I can go ahead and write that as my y-intercept. 1.69 would be right about there. At 2, we're at 3.48. At 4, we're at 4.09. At 6, we're at 4.47. And at 8, we are at 4.74. So let's try to plot these points the best we can. 2 is 3.48. 4, 4.09. 6 is 4.47. 8, 4.74. So we get something that looks about like that. We can connect our dots to the best of our ability. There we go. There we go. Don't forget that arrow again, right? Even though the graphing calculator doesn't show it, you need to know it goes to negative infinity. And there we have our graphed logarithmic function. All right, that was a lot of notes coming at you. Hopefully we're feeling confident. And if you want to see us do some more practice graphing logarithmic functions, you are welcome to check out the sample problems. Otherwise, go ahead and get started on those practice problems. Be sure you're feeling comfortable with your graphing calculator. If you have any questions about the graphing calculator, be sure to reach out during class. I'd be happy to answer those. All right, this is Mr. Carter signing off. I'll see you next time.